Discussing about the code 18 PYP102J, that is the mechanics of solids. We have discussed a few topics related to this code in my previous videos, and in the last lecture we were discussing about the shear force and the bending moment. So let us continue with the bending moment. So the bending moment at a section of a beam is defined as the algebraic sum of the moments of all the forces on one side of the section. So to understand this, let us draw a diagram of a beam of a member of the structure. Let's say a beam. So let us draw a diagram. So let us consider a member AB, which is simply supported at 2 points, that is A and B. A and B point, and carries 4 loads, that is W1, W2, W3 and W4. These are the 4 loads which the member is carrying, and the reactions at the supports are basically represented by R1 and R2. If we will cut the section into 2 parts, from this point if we will cut the section in 2 parts, so from this point we have cut the section, this AB beam, at this XX section we have cut. So if the moment M about the section XX of the forces, of all the forces to the left is clockwise, so the moment will be like this in the clockwise direction. For the left section, let's say the moment is M now. Then for the equilibrium, the moment of the forces to the right of the XX section must be M, counterwise. Mean to say, to balance this moment on the right section, we will have a moment M. So if for this particular section, if the moment is clockwise, then for the equilibrium, the moment for this right section should be counterclockwise. The bending moment is considered positive if the moment on the left portion is clockwise. This is clockwise, then we will consider it as it is positive. The bending moment will be positive if this is clockwise for the left section, and for the right section if it is counterclockwise, then also we will consider it as the positive. So if it is inverted, then the sign convention may get changed. So now if the member tends to cause concavity upward, mean to say here the member will be like this. So if it tends to cause the concavity upward, so this is usually referred as the sagging bending moment. And if the bending moment causing convexity upward, so that is taken as the negative bending moment and is called housing bending moment. So it is clear now what exactly the bending moment is. So we can say it is the algebraic sum of the moments about the section of all the forces on one side of the section. So let us now discuss about the relation between the load, shear force and the bending moment. So let us consider a small length of a member cut from the loaded beam at a distance x from a fixed origin point. So let me draw the diagram. If this is our member, so if it is a beam, and to understand, let me use this portion. So we are considering for this small part, that is delta x. So here it is delta x, the length from x at a distance x from this point. We are considering this small length delta x from the origin. Let's say the origin is here, it is O, and this is the centroidal axis of the beam. So here we may consider it as a symmetric kind of the beam. So we have cut this small part delta x out of that beam. So if the load is applied here, we can say if the W is the mean rate of loading of the length delta x. So the shear force which will be applied in the clockwise direction, in upward direction, this is our shear force for this part, and the moment will be like this. We may represent it by M, and the shear force due to this section, that is F plus del F, and the moment, that is also M plus del M. So now I think it is clear that what exactly the W is. W represents the mean rate of loading of the length delta x. This length delta x. F is the shear force. F plus delta S is again the shear force at the section x plus delta x. At the section, here is the second section, this is the first section. So for this section the shear force is F, and for this section the shear force is F plus delta F. If M is the bending moment at this x section, similarly here M plus delta M is the bending moment at the section x plus delta x. So the total load on the small length is equals to the total load on the small length, that is equals to W delta x, acting approximately through the center C. Here we may consider this through the center, this C. So for the equilibrium of the elements of this length delta x, so we may equate the vertical forces. So the vertical force F can be written as F is equals this force plus this particular force, this one. So vertical force is this force and this force. Okay, so this load, this small, the load for this small length plus this particular force. So that is F plus delta F. Okay, or we can say W is equals minus dF by dx, del over del x of this force. That is the rate of change of shear force. This is the rate of change of shear force, and that is equals to the intensity of loading. So now taking the moment about the C, taking the moment about C. So we have this M, this particular force from this, so the distance will be del x by 2, and moment M, so M plus F into del x by 2 plus this particular force at again the distance from del x by 2 plus this particular moment. So this, the sum of algebraic sum of this should be 0. So let me write it. So this is the total moment about C. It is M plus F del x over 2 del x by 2 plus F plus del F into del x by 2. This is the moment for this second section. This is for the first section of the shear force, moment due to that, and the moment due to the second section, and the algebraic sum of that is equals to 0. So if we will simplify it, so that is M plus F del x over 2 plus F del x over 2 plus del F into del x upon 2 minus M minus del M is equals to 0. So this term will be cancelled out, and neglecting this particular term, as these are the very small quantities, and the product of that these quantities will be much more smaller. So we may neglect this particular term. This term we will neglect, and this is equals to F into del x. Half of this and half of this is F del x minus del M is equals to 0. Either we can say that the force F can be written as it is del d by dx of M. So let's say this is equation number, next equation, whatsoever the equation number we are using. So this is the rate of change of bending moment curve is equal to the shear force. So at a point where this particular value of d by dx of M, dm by dx is equals to 0, if dm by dx is equals to 0, that is the shear force is 0. Mean to say, then F is also equals to 0. So where the shear force is 0, the bending moment will have the maximum value. Okay, so the point of 0 bending moment, that is where the type of bending changes from seizing to the housing, is called as a point of inflection or contraflexion. So now by the integration of the first equation from B to A, between the two sections A and B, so we can say that F A to B, that can be written as from equation number first, that is A to B, we are trying to integrate this value del dx omega the w dot dx. So which is the area under the load distribution diagram. So this is what, this is the area under the load distribution. So for the section from A to B, if we want to determine the moment also, so similarly integrating the second equation, that was your F is equals del dm over dx. So integrating on that equation with respect to x from A to B, so we can have the moment, that is MP MA is equals integrating from A to B F dx. So this shows the variation of bending moment between two sections that is equal to the area under the shear force diagram. So we can say like F is equals dm over dx, and W, that is the load, is equals to df over dx, or we can say it is d2m upon dx2. So these are the relation between the shear force, load and the bending moment. So hopefully you are getting this relation between these different quantities that we have discussed in my previous videos, previous lectures. So thanks for watching. Thank you very much.